So this afternoon I want to go into the submarine realm, right, but without an ROV, or any expensive kit or anything like hiring a ship or so on. We want to look at the on-land, right, well-preserved submarine volcanic hydrothermal system of Milos Island. And we want to have a look at how sort of processes within that environment, right, modify mineral deposits. Before I talk about the geology of Milos, right, and the mineral deposits themselves, I want to kind of revisit the context for shallow submarine mineralization. Right, look at some mineral deposit models, right, where they occur, right, what the main differences are between them, right, and have a look at the Aegean Arc tectonic setting where Milos is located. These are two classic models. We've seen this one many times today. That's the porphyry model. And this one is stuck out on mid-ocean ridges, right, and never the twain shall meet. This is based really on looking at on-land, right, continental arcs. Right, this is based on ocean ridge systems, and they're fundamentally the models that we use, right, to look at a variety of styles of mineralization. But a lot of arcs, right, have both a submarine and a terrestrial component to them. It's just the Kermadec arc, and the Taupo volcanic zone is here, and this is the classic example of on-land epithermal mineralization. This is the Aeolian arc, and this has submarine, right, seafloor massive sulfides in Palinuro, right, and Panarea. And this is the Aegean arc, which has, volcanoes at Santorini. And there's a small volcano that's just to the north of Santorini, which is in the submarine realm, and that's Colombo, right, and that contains mineralization. And so when we think about these, when you think about these sort of systems, right, we have to think about where they are and where they're located. So here's Colombo, right, and here's the Brothers volcano. The big difference between these is the water. This is in 500 metres of water. This is in 1,500 metres of water. And I've put this up here to remind me, this is White Island, right, and this is the type example, right, of an active porphyry system, allegedly, but most of the porphyry system must actually be underwater. And the big difference between these two is here you get lots of black smokers and sulfides, and precipitating sulfides on the sea floor. Here there's lots of gas bubbles. The water depth here, right, stops the hydrothermal fluids from boiling, whereas here they boil, and what you see at the sea floor, right, is the hydrothermal gases that come from that. So the Aegean arc, right, Milos is here, that's what we're going to go and have a look at in a minute. Right, but backing that, right, is the Kyklaves core complex, and just off the north here, right, is Skouries, which is a porphyry copper, and Sapes, which is an epithermal gold deposit up here. These are related to another core complex, which is the Rhodope. That's quite old, that's sort of Miocene. This is kind of still active, and extension is still going on. So now I'm going to talk about a little bit about Milos itself. That's a spoiler alert for some people in the audience. So some background geology and the overview of the volcanic facies. So Milos itself, it's quite to break the geology down to simply, it's built on explosive pyroclastics and a number of volcanic domes, right, from rhyodacite, dacites, right, and some andesites. And the area we're going to have a look at is Triaves, and I'll come to that in a minute. So the basal pyroclastics, this is probably a single eruption, pumice breccia. At the very top, you'll notice the inverse graded bedding. This is due to sort of water saturation. So these are more buoyant in the water column than the material down here. And this is typical right, for the whole line. This perhaps is about 20 to 30 metres thick. And within that, you get large sort of pumices, right, and these lie on marine sediments with a variety of marine fossils in them. So there's no doubt that these, right, are submarine in their origin. And then within that, there are large cryptodomes which intrude and extrude these sequences. And here's one in here, and you can see the flow banding in this. And again, this is the basal sort of pyroclastics. And in the cores of these are coherent, right, and have lots of columnar jointing. I thought I'd show some pictures of geology after a whole morning of graphs. And this is the contact. Here's the dacite. And you can see here the sediments, right, are banked up against that, because they've been pushed up and inflated. And locally, this is a lava dome in here. You can see the fingers of it. These are associated with advanced argillic alteration. This is, I think Jamie showed, sort of like a lithocap. So this is potential lithocap. I'm not going to talk about this in detail today. And if you wanted to look for a porphyry, this is kind of where you would go. And it's intrusive and diffusive. So here's sort of like the zebra rock. This is the basal tuffs. In here, that's sort of like andesitic material. And these, right, are actually wet when these were intruded into. And along here you can see sort of mingling of magma and sediments. So this is a highly sort of active environment. And then you can see this in here, right, it's just a mixed rock of dacite and pyroclastics, but you can see in here, this particular thing has cooling cracks and a chill margin, so that was magma at one stage, so this is kind of like a peperitic rock. One of the things that happens within this is the slopes are really steep. So here's the basal pyroclastics. And there's a raft of that caught up. It's been ripped up. And this is sort of a debris flow, right, from a coherent lava dome that's further up the hill. And that's kind of like the background geology, right, within which the mineral deposit sits. I'll talk about the mineralization at Triar. There's which is lead, zinc, silver. And what this represents is a kind of an exhumed landscape. So here's the core of the lava dome, the pyroclastic apron that sits around it, and then within these, right, are individual sort of like little breccia pipes. And we'll have a look at these in a bit more detail. So this represents sort of exhumed submarine topography that we can now see how it used to look perhaps 2 million years ago. So here's one of these breccia pipes, and this is nearly 90% barite, and these are rootless in the sense that if you go up to underneath them, you can't see any stockwork that sits underneath them, so they're quite enigmatic about how they form. And when you go and look at them closely, you can see up they're made of boulders of barite, sort of loosely packed. And on the individual barite class, you can see new crystals of barite. So mineralization, so that barite has moved, it's been eroded. Mineralization has continued and precipitated more barite on the barite. And in some places, there's a hint, right, we might actually get some sulfides within sediments. We've got to have a look at these to see whether they are. And this is a typical. There are also those breccias that have been transported, and then there are these breccias, right, which are in situ, and these are highly silicified and still where they are. And if you look at these again contain class of barite, veined by quartz, and classed within class structures. And this is a typical, so we also get silicified breccias. These individual clasts are about 1 to 2 centimetres across. You can see the pencil on there. And then occasionally you get sulfide veins. This is a galena and sphalerite vein, which I'll show some ore petrography of it in a minute. And this is what they've been excavating. So this is what's left now, and this is what they've mined out. So I presume at some stage that was another vein. And to the right here, you have breccia, which contains mixtures of volcanic clasts and barite and sulfide-bearing clasts. Mineralization values typically sort of barite, quartz, galena, sphalerite, with bits of tetrahedrite, which is silver-bearing. Occasionally the sphalerite has chalcopyrite disease, here and here. Other places you get a lot of pyrite, you sometimes get development of chalcopyrite, but chalcopyrite is never kind of extensive in any of this, and there are reasons behind that. And there's also the indication this is galena and quartz, and it's dendritic, so there's rapid crystallization from supersaturated solutions. Coliform textures. In here, this is tetrahedrite and silver-bearing, sphalerite, and a little bit of chalcopyrite. And in terms of the alteration that sits around that, it's adularia, which is important for indicating in terms of whether the system is boiling or not. Sericite, and this tells you neutral to alkaline or fluids, and this is ubiquitous. And so a little bit of a diversion is that the schematic, Milos has an active geothermal system, which is located perhaps 1 to 2 kilometres from the surface. It's hot, 300 degrees, and you get phase separation from the top. It's a brine sort of lens, but this brine lens isn't a magmatic brine lens. This is seawater. And the deep reservoir has 9% salt. Strontium isotopes not shown here, but in papers that I've published show this is modified seawater. But there is always a hint wherever you go around here that some of the volatiles like boron and sulfur indicate periodic injection of sort of magmatic fluids. So I had a look at some of the fluid inclusions from Triades. It's got 3 white. Again, if you think about the people say, oh, this is a magmatic fluid, it's mixing, you expect them to be hotter up here with the more saline ones, but they're not. It's a trend that runs in that. It's boiling and vaporization. Some things down here may be condensates. And importantly, within this, there's sphalerite. So we know that these are actually, this trend here is actually the ore-forming fluid. And if you take sort of down here, 3.5 weight %, this shows the depth of water is probably about 200 metres. So these are in the shallow submarine environment. Not my work, but paper published by Marchik et al. I recalculated theirs to the same temperatures that we got, 210 degrees. And so you see that current Milos geothermal waters, that's current seawater, that's strontium in the sphalerite. So this indicates we're definitely in some sort of submarine environment in case you thought it was otherwise. And the volcanic rocks are up here. So to kind of summarise what we've seen, we've got a dynamic volcanic environment with evidence of mass transport. Transportation of barite class in a sedimentary environment and sulfide class. Sulfide mineralisation is mostly fault-controlled, sub-sea floor, but there's some evidence of seafloor mineralisation. The mineral fluids are modified seawater. And I think I'm just about to finish up. This is the last slide. So I have a conceptual model. Fish to tell you where you are. So these lava domes obviously controlled by faults. And you have mineralisation occurring in the carapace of these, and sometimes it stays in place, but this can then be transported down and eroded off. And unfortunately, this has not good prospects for the long-term preservation of mineral deposits, in the sense that unless you've got somewhere, a basin somewhere in which you can accumulate all of the sulfides and the material, it will gradually get sort of weathered away and moved off. Okay. That's me, thanks.
When I got here yesterday, John was worried that he had too many slides and he was going to overrun. He's obviously done quite well because we've got plenty of time for questions now. So,
Or any coffee.
yeah, or an early coffee. Does anyone have any questions for John? Yeah, so, come on, Debbie, off you go at the back there.
You just in it and then walk the maximum possible distance. You have to walk down there.
John, so my question, obviously we've worked on it, but if Milos is going to emerge, how do you, in your model, I mean, how do you think that sort of changes dynamically between here and the point where it's actually emerged and the stuff is coming out in a subaerial system? In other words, is there any important transition between sort of this stable sea setting and on the way up? And does that matter for any part of Milos?
Well, in this particular environment, as I said, now, any collapsing of the volcanic edifice will have no impact on the mineralization because the water column is the same. But once you get into the subaerial environment, and if things change, you get sector collapse, that then changes the hydrology of the system, and enable telescoping. So the other thing that you don't get here is telescoping of epithermal systems where they sit on top and uplift causes the mineralization to be extended over a large area.
I guess I also mean, you talked about 1,500 meters versus 500 meters. So how much does 500 meters versus 200 versus 50 meters matter in terms of the way the fluids behave here? Or is that actually irrelevant? No. Okay.
I mean, it will move. It doesn't make a great deal of difference.
Anyone else? Nope. Okay, so we've got one. Oh, sorry. Yeah, you're in my peripheral there.
I stood in the way.
You mentioned right at the beginning that White Island was a site of an active copper porphyry.
That's according to Jeff Higginquist or whatever.
And what's the evidence for that?
I think they measured the copper coming out of it and did some calculations.
Isn't that the opposite of a copper porphyry if all the copper's coming out?
That was some. I mean, that was kind of an example, sort of an example of that in this particular environment. I mean, if you want to consider porphyry coppers, they don't just occur in the high Andes. They can occur that particular model. What does it look like when it's under 200 meters of water? Are the systems isolated from seawater? Then you're kind of okay. You don't have to worry about it. But if they're not isolated from seawater, that's one of the largest reservoirs of chlorine, and how that affects things and modifies things. And again, when you get the collapse of the hydrothermal system, you're not getting meteoric water that's going into it, you'll be getting saline water.
Just to make it more apart from the fact you've got a slightly different magmatic system, a lot of the elements of what you've just talked about is very similar to sort of your classic Irish type deposit. You've got, I mean, you make a face like that, but you've got mineralizing fluids which are fault controlled. You've got zinc and lead, and you've got sort of you've got seawater brines. You've got epithermal mineralization. Have you considered that as a bit of an analogy? From the silence, I'll say no.
I mean, to be honest, no, but I was thinking about why it isn't. There is evidence, of magmatic fluids in the system, There isn't in Irish-style deposits. Some Irish-style deposits are very, very different in terms of the types of fluids that are in them. For example, basinal brines, or if you think like MVT style things. The mineralogy may in terms of the sulfide mineralogy may be similar, but I think that's probably because of the chlorine, it's the main complexing ligand, and the salinities are sort of similar. But that is associated, so no, it's a different kind of geotectonic or dynamic geodynamic environment.
Yes, yeah, I know, but just from sort of from your model here, I mean, I'm not talking about the large scale like Narval and stuff like that, but you've got a lot of peripheral mineralization systems where you've got shallow seawater, fault-controlled magmatic deposits where you've got fluids like this coming up into sort of shallow seawater type environments. I was just, there does seem to be quite a few different connecting points. I mean, I might have got the wrong end of the stick from your presentation, but from what I've seen, doing 4 years study in Limerick, there are a lot of...
They're not carbonate hosted.
No.
That's one kind of difference.
I meant the magmatic.
And they sit
style.
in a volcanic environment, and it looks kind of like if you go to Panaria, the same places like that, and there's seafloor massive sulfide mineralisation going on there. I think they're different. I mean, the Irish style mineralisation is related to opening of an ocean. In terms of the magmatic activity, this is related to the closure of an ocean.
I agree, the tectonics.
Yeah.
Tectonic setting's different,
Yeah.
but there are a lot of analogies which I think could be made.
Both extensional context, to be fair.
Yeah.